Okay, hello everyone. My name is Peter. I'm co-founder of a company that named OXORIO. So we do security audits. Mostly we focus for the last 2 years for Solidity, but now we also switched to ZK and found very interesting things that we want to share with mostly developers and everyone who want to know how to write the code, how to write it safe on Circom and different others languages that using ZK, and I want to show you what you need to point out in your code and how to make it safe, because it's totally different how you write the code in Solidity and in Circom and different other ZK languages. So the agenda is we will check the basic attack vectors that could be possible in ZK proofs and ZK circuits and the whole ZK systems. Also, I will show how to prevent these attacks and sorry, some like mitigation strategies, how to developers can fix it, and some other security approach that you need to check beside the code. So I will start from very basic things, but this is one of the most important and most common vulnerability. It's something like in Solidity, like reentrancy. We can find in almost half of our security audits. Reentrancy attacks becomes more complex, but still they exist. And I think in the circuits, this type of attack will be most common. So what happens just in case, I just want to get to know who is my audience here. Can there raise a hand who is a developers? Okay, good. Who write the code on Solidity? Great. Yes, and like who know what is the circuits in terms of ZK? Okay, less, but I will explain it a little bit more. Good. So the circuits basically is some programs that mostly from the developer perspective it's like close to the functional programming. You work not with the just variables, it's more like a signals. It's more like traditional circuits that you have just like circuit. So you, I don't know how to say it in. Yeah, it's more like a functions, and you work with the signals. So under constrained circuits, it means that you didn't check the inputs and outputs correctly. So you need to check and verify that everything that you put into your code is valid. So usually you just put the like some bytes into the input, and there is if you didn't check that it's correct, so verifier can prove something that doesn't anything. I will show you an example. It will be easier. So this is one of the most important things, just to not get messed with the circum assignment operators. So if you do something like this on the left, it's just assignment. It doesn't do any kind of checks in your code. If you do like this assignment, I don't know, point, yeah. So, so this is a constraint. So if you want to check that something is constrained and satisfies some some logic in your code, you have to use this kind of constraint. People can just mess with this very easily, and it becomes a lot of issues with that. So, like as an example, this is a very basic code. So here is a like like hello world. You have three signals, and you want to prove that you know like factor 1, factor 2, and you know that if you multiply them, you will get the value 3. And when you do these checks, like basically this is a single line proof that you can use, but you need also to remember about many different things that you have to check, like that the factors are not equal to 1, so you can just very pass through the checks if you will just send not like factor just 1 here, and factor 2 will be equal to value, and you will just pass and prove something that isn't correct. I will show you. So how to mitigate these things? Here is a code, like basic that we. This is a real issue that was in one of our code that we audit. So if we just check these outputs, we need to add extra checks with it looks like this. You convert component in num2 bits and work with this amount of bits. Okay, sorry. I think this I just get messed with the several slides. It should be. It's very hard to explain because I just skip several slides. Yeah, that's why. Okay, I will just come back later to this. So yeah, so first I want to tell about arithmetic overflows. So when we work with the circuits, we working with the elliptic curves and with finite prime fields, and you need to know, like, if you just do didn't check the overflows, so you need to check that all the values that comes into the signal is less than your prime number of your prime fields. It depends not of your code, and it depends to the proving system that that you're using for running this code. So you need to check the proving systems and what kind of cryptography is under the hood. So this like very basic example about how it works. For example, if your field order is for example 100 and you have a value like 10, and you can just simply get the two factors like and pass 110 instead of 10, and it will pass the validation. So to mitigate this, so you can check this component that works with num2 bits, a special function that checks that your signals doesn't exceed the maximum maximum number of your prime field. So this is a real example from Tornado Cache and code, and it was a semaphore issue that was in the library named Semaphore. So it was in 2019. It appears in many libraries that using like circuits. Nobody checked that the maximum amount is 2 power 254 in growth 16, and in classical solidity code you have you int in 2 power 256. Because of this, you can just easily do double spend attack for Tornado code. Luckily, they found it before it get to the live. So this is the issue. You can just check details. Like Roman Semyonov, one of the developer of Tornado Cache, found this, and later a lot of researchers did a quickly fix for their code. Some of them was in production. So there's like Socrates, Miximus, and Snark.js. This is a very common library that was popular at that time, and they're all was affected by the same very simple things. The simple issue with the maximum number that you can use in this elliptic curve. Yeah, so how to mitigate? You need also to think about your signals. Is not like it's just parameters. It's like number of bits. So you need to also to check bit length, and because they can just be simply trunked in your code if you didn't do special checks. For example, here I think it's not easy to check this code, but the simple thing that if you pass like 001 or 1001, it could be both of these things will pass in this code, and it will get you the wrong proofs. So how to mitigate this? You just need to do these checks with num2 bits, again with max bits. Another thing is mostly related to the compilers. Maybe it's like it's bug or feature, but compilers can remove unused inputs that you don't use in your circuit. For example, again, in Tornado Cache, they are using some inputs to check the data of relayers who will operate with the proofs. And in the beginning, when they start to use it, they realize that you can put any kind of inputs into this unused inputs, and proof will be valid. Like you can just do as many proofs as you want. So for now, there is no any compiler flags that you can use, so you can just do some workaround and add some fake calculations. That's it, and like multiply this input by itself, and then this thing will be preserved in your proof. So another thing is very basic, but I need to mention that please don't use your own cryptography. So many developers try to implement and improve some cryptography functions. It's a very bad idea, because there is so many caveats that just normal developer can't realize that it will happen. So I can recommend to check zkdocs.com. It's a website from audit company Trail of Bits, and they have very good examples how to mitigate some issues and how you need to use, how to work with the cryptography functions, what you can do with them and what is prohibited. So here is some kind of example with Fiat Shamir. So if you just use the function, please don't just put it in, just check documentation. It's super serious and important in ZK especially. So also now you can see that so many proving systems appeared, and they are still in research stage. So most of them are not audited or verified, and even if they are very promising and you think it will improve and give you competitive advantages in front of others, please don't don't use it, because later I'm sure we will find so many of them are not ready for production code. So like things like growth 16, this is a proving system that works in most ZK solutions that we have. It's very good stable things, but not very convenient. So because we have a Hala and Plonk and other things that now also in production, they have also like folding schemes, they have pairings and everything that you need to improve your system. You can use them, but for new researchers, like just don't take it if you see it's just faster. Okay. One more thing about trusted setup. This is the basic thing. Who know what is trusted setup? Okay, so most of all of you. So in 2 words, it's just the thing that you need to do before you start to use your verifying system. There was issue in Zcash in 2019. This is, I think, one of the biggest and older company in blockchain that using snarks, and even they miss some parameters in their trusted setup mechanism. So they did it very well. They put their computers in the Faraday cage. They destroyed their computer after they did trusted setup. But the issue was that some parameters leak not through the MPC, like this trusted setup solution, but by the some extra data that before they assumed that they are not related to the trusted setup, but later they found that from the final parameters of this trusted setup you can recover all these things, and you can simply just do validate whatever you want on Zcash. They fixed it. They say that nobody exploited, but now we don't even check it because nobody knows what happens there. So the latest thing, I want to check some example from our latest audits of privacy pools. So privacy pools is like next generation of Tornado, but then they fixed the thing that you can prove that your inputs or outputs are not in the list of some hackers group. So you can create some dedicated list of inputs and say, hey, my transaction in this list or not in this list. So you can separate yourself from hackers and prove that your money doesn't related to money laundering, for example, which is super useful and could bring the privacy to the people without any obligations that now we have with Tornado. So very interesting thing was in num2bis manipulation. So this is a complex bug that related to all the things that I showed you before. First, they improve num2bis function. So actually they try to write their own cryptography. Don't do this, please. The second thing, they mess up with the constraint thing. So they just assign operator instead of do the constraints. So technically, you can just give here any kind of inputs, and it allow to the prover substitute input that's originally like user give to the prover and generate the valid proof from invalid data, or do the opposite. Very simple thing when only one you can just do one-liner fix, but this thing can break the whole system. So just and they just try to, I think, optimize like num2bits and do some tests inside. So don't do this. Okay, so besides this, you can use this set of tools. There is some static analyzer. Some of them try to do fuzzing with the ZK things, and some tests use that cover circuits. I highly recommend to use them because for now it's not easy to write the tests on the circuits, but if you don't write it at all, it's very hard to support these layers as usually in development. So in conclusion, so programming with the ZK snarks, when you do this, just keep in mind this is a signals, this is elliptic cryptography, and you need to check the math behind that. It's not just a normal code. So check the bugs and most common things that you can find in the internet and check what was wrong with them. The most popular is under constraint circuits that I told you, arithmetic overflows, and you can check like frozen heart and trust setup leak. This is the things that's related to Zcash issue, and some other things you can easily find. This is a lot of information you can check later. Also, try to subscribe to some ZK groups because there are so many things happens there, and ZK technology updated every month or 3 months completely. So is very fast-growing ecosystem that development even faster than Solidity. Uh, so just check it, because if you not into this, you can easily miss very important things. For the groups and the reference, you can ask me. So also, if you have some questions, so we can talk later, I will be happy to explain you some details and how to work with the circuits. There is also, we explained the Circom, but there is also Kyra, Neuer, and different type of languages. So they are bit more complex, but they are newer and have some extra benefits for the developers. They have very fast-growing technical development ecosystem. Yep, that's it. Thank you. And your questions, and welcome to ask.
Yes.
I thank you for the talk. Maybe like a naive question, maybe I not fully understand the whole like picture, but when you describe the overflows and underflows, like looks to me like a issue that should be solved at the type checking level. So why isn't this solved at the programming language levels like Solidity? Why am I even allowed to make a subtraction from A to B where B is larger than A?
So it's because of when you, I think the good example is, so Circom is like a circuits. And there is some kind of software then you can write on right on top. You never know what kind of software and hardware will be compatible and not. You can just constrain the like size of your inputs, because if you use different proving system, there are different numbers, and if you using recursive snarks, you can also need to work with different math approaches. So it's not easy to like just simply constrain these things in the circuits. Even in Solidity, how many years passed before safe math became a standard? So I think 5 years, and only in Solidity version 8 they fixed this, and before everyone used safe math, which is like external library. So same happens here in circuits. You just need to check. Maybe later, when there will be some one single standard, they will put it into the into the framework, and you don't need to check. But for now, it's all rely on the whole thing. It's like a Lego. You can just build your own from different kind of system, like proving system and language that you use, DSL, and so on.
So like, is it possible to make like? So is it would it be possible to implement something like safe math on the circuit level, such that I can use the circuit and write these like programs as you described, without like, if I have A and B and their meaning is like some balance, then it is positive by definition, and I don't have to check it, because it's kind of by definition they cannot be lower than 0, for example.
Yes, actually, you can do this, and there is some mathematical functions that's already implemented. But the thing is, usually all the calculations that you do is very unique, and you always have to change something in them. But of course, there is functions like less than, more than, and num2 bits is very basic function that just check this overflow. You can put it in the more complex circuit. But since you try to optimize everything that you can, usually there is no reason to make a complex function if you will use only several checks from them.
Yes, do we have more questions? Don't be a stranger. Raise your hand. Anyone? With that being said, let's conclude this session, and thank you, Petr, for sharing the knowledge with the community.